Today we will start a new chapter on our topics. The new chapter is solid state phase transformations. We have been so far talking about mostly on liquid to solid. You have seen this so far. We talked about solidification, melting. We even talked about isomorphous solidification, we talked about eutectic, we talked about peritectic solidification. We even went to the extent of how a liquid becomes a glass, and we also brought in a T naught concept in the meanwhile, and so understood what is called metastable phase diagrams related to that. So today let us bring in solid state. So the moment you talk about solid state, that means one solid giving you another solid, or one solid gives you S1 gives you S2, or S1 gives you S2 plus S3, variety of transformations. What are the solid state transformations that you are aware of? Eutectoid is one. Eutectoid is something like this one. You can call this as a eutectoid transformation. So the well known eutectoid, Anisha, which is the eutectoid that you are aware of? What is the type of transformation? What gives iron plus cementite? What gives alpha plus? What is the eutectoid reaction in iron carbon diagram? Gives correct. So the austenite gives you ferrite plus cementite. This is the eutectoid in the iron cementite phase diagram. This is we are aware of. Any other solid state transformations that you know, Prerna? Solid state, where something in the solid state gives you something else in the solid state. Anybody else? Alpha to gamma, gamma to delta. This is something like this. Okay. What do you call them as? There is a name given to such transformation. When alpha goes to gamma, let us say alpha iron becomes gamma iron, they are called allotropic transitions. They are called allotropic. Okay. And the same thing if it is happening in alloys, we call them as polymorphous transformations. Allotropic transition is the term which we use in case of pure metals, or even for example in ceramics. You must have heard of alumina. Alumina exists in different structures, gamma alumina, alpha alumina. These are all allotropic transitions. Even silica, cristobalite, and variety of forms. Titania, TiO2. Many people are aware of nano titania particularly. Nano titania, do you know what is the particular purpose people want to use nano titania? Self cleaning. Okay, is all nano titania nowadays. Okay, so that is just one of the application. Nano titania, in titania there are allotropic transitions. What are the most important allotropic transition in TiO2? Anybody knows? Anybody who is attending any ceramics class? Rutile to anatase, anatase to rutile, that is another transition. These are all allotropic transitions. There is no compositional change during this, only structure is changing. Okay, we call all of them as allotropic transitions. And in some alloys also you can have transitions where composition does not change, only structure changes. We call them as polymorphous transformations in general, and usually in practice we use the term massive transformation. Why we call them as massive is because such a transformation is very fast. Why it is very fast? Because it does not involve, he is right, it does not involve long range diffusion. You cannot say it does not involve diffusion. Are you aware of any transformation where it does not involve diffusion? Martensite. So that is the next type of transformation, which is where you have Martensite. So in fact if you want to talk about solid state transformations, we can solid state transformations can be basically divided into diffusion based and diffusion less. This is simply one way of talking, and diffusion less is what is called Martensite. And in diffusion you have short range diffusion and long range diffusion. All those short range diffusions are these allotropic transitions, and you have one you can talk about massive. Any other transformations that you are aware of which are short range diffusion? Where the diffusion distances are not more than a few interatomic distances, maybe a 1 unit cell, maybe a few unit cells. Order disorder, very good, order disorder. So these are certain transformations which are basically a short range diffusion transformations. Anything else that you are aware which is again short range? Spinodal, okay. Spinodal transformation again is a short range, at least at the nucleation stage, and as it progresses it grows. So spinodal also more or less can be, at least initially at the nucleation stage it is very short range. And then long range diffusion, what are the things that you are aware of? One you just now said, what did you say Anisha? This is the transformation you talked about. We are talking of eutectoid, do not say eutectic, eutectoid. So eutectoid, this is the one. And anything else that you are aware of? Peritectoid, okay, fine, let me take it. But there is something which you are commonly aware of, and precipitation, very good. Where an alpha supersaturated solid solution gives you alpha plus a precipitate, you call it as let us say theta in case of aluminum copper, in case of something else you can talk of something else. So many types of, even in steels we have a precipitation. What is the precipitation that you are aware of in steels? In a plain carbon steels, what is the precipitation that you know in plain carbon steels, which is regular? I mean all of you in second year BTech metallurgy have come across when you are talking about heat treatment of steels. In heat treatment of steels, lead is not related to that. Yes, somebody murmured some word just now. Yes, what is the precipitation that you know in steels, plain carbon steels? During heat treatment, one particular type of heat treatment it happens, it is not in alloy steels, tempering. Yes, the epsilon carbide formation in tempering is again that, where martensite with a particular carbon content gives you initially epsilon carbide and finally cementite, is not it? So that is also a precipitation, where one structure with a certain composition leads you to a precipitate with a different crystal structure and a different composition. The epsilon carbide is what is the composition of epsilon carbide, anybody knows? Fe 2.2 C, 2.4 or 2.2 C, this is what people talk about. So that means definitely its carbon content is different from that of the steel martensite from which you are starting. So you and its structure is, what is the structure of epsilon carbide? Yeah, somebody said, tell confidently, whatever you say confidently, that is important. You are an IITian. Yes, somebody said it, you only said possibly, somebody just now I heard the answer, but he was not confident. Whoever said, he has said right answer, but he is not confident. Can you repeat what you have said? Who you said? No, HCP. So it is hexagonal. Okay, we will talk about this, why hexagonal should come out, we will talk about those. So that is all the precipitation. So it is a cement martensite, which is, let us say, a body center tetragonal structure, gives you BCC alpha plus the epsilon carbide, which is hexagonal, and then this epsilon carbide, as it grows slowly, it becomes orthorhombic cementite. Same thing happens even in aluminum copper. We are going to see now that it first gives you GP Jones, and then slowly it gives you theta double prime and theta prime, and finally the theta. We will see why this sequence has to be maintained, that also we will try to see. So these are all the long range diffusion, which definitely are the order of a few nanometers or a few microns, depending on the grain sizes that we are talking about. So these are all, if you want to generally classify solid state transformations. We will try to take some of them and then see how we go about it. We will start with precipitation. This is a transformation which commercially also is a very important transformation. All edge hardening is all due to precipitation hardening, precipitation that we are all aware of. So let us look at precipitation and take the example of aluminum copper itself, the most popular precipitation hardening. If you remember aluminum copper phase diagram, particularly on the aluminum rich side, if you look at it, it looks something like this. This is how it looks like, and on this side, so there is the theta phase. This is how the aluminum copper phase diagram look like. Of course, theta is what stoichiometry is it? What is the composition of theta? CuAl2. So it is basically Al2Cu. So Al2Cu basically means, if I am writing percentage copper on this side, how much is this? How much copper? 33.3% what? It is weight percent? It is atomic percent, correct. So this is atomic percent or mole percent, whatever you want to call it, because Al2Cu, one atom of copper and two atoms of aluminum, and if you convert it into weight percent, actually it comes close to about 50%, because atomic weight of copper is almost even more than double of that of aluminum. Aluminum is 27, I think 63.5 is copper. So if you consider that, it comes out to be much higher. So anyway, so this is pure aluminum on this side, and when we are talking about precipitation, what we are talking about is taking an alloy of some composition like this. And what is this composition? Anybody? I am getting different. Yes, it is approximately, anyway different books will talk differently, approximately 5.6%, but whatever we are talking here is weight percent, remember. So this is all, now we have to convert it into weight percent, whatever it is. So most of the commercial phase diagrams that we talk about are all in weight percent. So this is 5.6%. And what is this reaction? Anisha, can you tell me what is this reaction here? Eutectic, what gives you what? Liquid gives, what are the two types? And theta and, little louder, half of the word is only coming out of your mouth. Alpha. So liquid gives alpha plus theta, this is a eutectic reaction there. And we are not at the moment bothered about that eutectic reaction, which we have talked about it enough in the previous classes. So let us not bother about the eutectic reaction as such, and incidentally this particular eutectic is a lamellar eutectic. Aluminum copper is a standard lamellar eutectic, let us not bother about it. We are now looking at the solvus part of it. So look at this line, which we call it as the solvus, and this solvus, if I look at it and take an alloy of this composition, let us say 4% of copper, that is a standard alloy that we talk about, and if this alloy is heated to this temperature, what should you get if you heat it to that temperature? It should be alpha, completely alpha if I heat it to that temperature. Now if I take it to that temperature, cool it slowly, what should happen? Yes, by the time you reach this temperature, once you reach a temperature below that, theta should start precipitating out of alpha. Why? Because the moment I come to a temperature like this, if I come to that temperature, at that temperature the alloy composition is 4% and the solubility of copper in the alpha at that temperature, if I draw a tie line, solubility of copper in alpha is this is this value, and because alloy has more copper content than what it can dissolve as a solid solution, this excess copper should be rejected out, isn't it? That is the whole principle of precipitation. And where does this theta come out? Where does this theta come out? At the grain boundaries, that is what it is. So if I look at the microstructure, if I say this is alpha, all are alpha grains, then you will see that in principle the theta would come out at the grain boundaries like this. It will nucleate at basically at the triple junctions, at these points. These are the junctions where the nucleation starts. Again we will try to understand why should the nucleation start at these triple junctions. That is where we need to understand that whenever we are talking of a precipitation, alpha giving you a theta phase, this precipitation always should have certain driving force, and then because any transformation has an activation barrier, it has an activation barrier too, similar to liquid to solid, it has an activation barrier too. And in this particular case, whenever we are talking of a liquid to solid, the activation barrier that we talked always is what is called the interfacial energy, isn't it? So that is why if you remember we wrote an expression, the delta G for the transformation liquid to solid is for a spherical nucleus, we wrote it as 4/3 pi r cube delta GV plus 4 pi r square gamma. This is what we have written for the solidification, and we said this is the barrier for nucleation, and whereas this is the driving force for the nucleation. Am I right? You remember all this. Now when I am talking of solid state phase transformation, you have another barrier which comes out, that is called strain energy. When a structure which is different from that of the parent phase is nucleating inside the parent phase, there is a structural incompatibility between the two, and as a result certain strain is generated. Even if the structure is exactly the same, if the lattice parameter of the precipitate is different from that of the lattice parameter of the matrix, you will see certain strain, and that strain is more of a volume in nature, it is volumetric. So that is why it is you have to add 4/3 pi r cube delta G E, people call it as E or epsilon, because strain is usually represented by elastic energy. So either E is, people put it as E or epsilon there. So this is the, so in this you see this is positive, this is also positive, and whereas this is negative. For example, for this particular alloy, if I draw a free energy composition diagram, I can say G versus free energy temperature diagram. Let us say if I draw, I can say this is the alpha phase and this is the theta phase. Let us say if I say in principle theta is at low temperatures, let us say. So in principle, so this is the theta, this is the alpha. If I say below a certain temperature there is a driving force from alpha to theta, at for every alloy there is a particular temperature. That temperature is what we call it as, what do we call that temperature? For every alloy there is a particular temperature below which the solid solution wants to give a precipitate, wants to precipitate out another solid phase. What do you call that temperature? It is called Solvus temperature, as simple as that. It is the Solvus. So this is the Solvus temperature for that 4% copper. If I am plotting G versus T for both alpha and theta, that particular temperature is the Solvus temperature, which is this temperature in principle. And if I write what is called free energy composition diagram, G versus X diagram, we have again two phases, alpha and theta. So you have an alpha phase, free energy of alpha phase, and you have a theta phase, and theta being an intermetallic compound, okay, it is more narrower, its free energy composition diagram, and it is supposed to be somewhere at 33. So let us not bother, consider this as the pure end, metal end. Let us say this is going towards pure copper. So somewhere you can put the theta phase, and if I draw a common tangent between the two, sorry, it does not look like a straight line, I will draw it once again for you. Okay. So that is so this is one composition, this is another composition. What does this composition correspond to? What is that composition? That yellow dot. Composition of alpha in equilibrium with theta. Where is it on the phase diagram? Which point? It is the Solvus composition. It is nothing but one dot on the Solvus line at any temperature at which I am drawing this. Before you ask me what exactly that composition is, you should ask me what temperature you are talking about. Depending on, if I am talking about this particular temperature, this yellow dot is nothing but this yellow dot. So these compositions that you get at various temperatures, which is nothing but the equilibrium between alpha and theta, are nothing but this. In principle, if I can draw alpha and theta free energy composition diagrams at various temperatures and get these compositions, this composition is not going to change, because this is more or less fixed, because it is like a line compound, its composition is fixed, though it is not really a line compound, it is very narrow range, composition range it has. I have just expanded for the sake of only our easy understanding, otherwise it is not a large composition range, it is possibly less than about 1%. So that is the kind of range, composition range that we talk about theta. So theta composition does not shift, but alpha composition is going to shift from here at room temperature to here at this temperature, and once I reach this temperature you will have to even talk about liquid also. Until that temperature is reached, where is liquid now? If in our free energy composition diagram, it is above these two, somewhere here. You have liquid also, but that liquid composition is somewhere like this. Liquid free energy curve is, it is above the 2. So the stable state is alpha plus theta, and the moment you reach this eutectic temperature, this liquid free energy curve comes and touches the common tangent between the alpha and theta, so that all three of them will have the same common tangent, and that is what is the eutectic temperature. Until you reach that eutectic temperature, you will have liquid curve always above that of the common tangent between alpha and theta, and the common tangent composition at various temperatures is nothing but this composition, and if you draw what is called the locus of all these compositions, what you generate is the Solvus line. What are the other methods of finding out Solvus line? How do you find out Solvus line? XRD. I hope all of you have done it, otherwise some of you possibly are doing this XRD course. There is one separate chapter in quality, please read it, which will talk about how to find out Solvus lines from that. So one of the most common method is XRD, of course there are other methods too we can talk about. So that is how you talk about it. Now what we are talking about is not this liquid, forget about this liquid. So we are now talking about an alloy which is having a composition between this and this. This is the composition of alpha in equilibrium with theta, this is the composition of theta in equilibrium with alpha at let us say this temperature T1, we call it as T1 here let us say, and at this temperature if I extrapolate this line tie line, wherever this tie line intersects here, that particular composition, this composition is this composition, am I right, and this composition, this yellow dot is this yellow dot, and my alloy composition is somewhere between these two, am I right. So that means I am talking about a composition like this, a composition between C alpha theta and C theta alpha. So this particular composition, the moment I look at it, this composition if it exists as a single phase alpha at that temperature, what is its free energy? How do I know? If this alloy exists as a single phase alpha at that temperature T1, what would it be its free energy? How do you get that? Can I get it from the free energy composition diagram? The intersection point, intersection point of this vertical line on the alpha curve will give you the free energy of alpha having that composition, and what is that point? That point is this, that is the free energy of alpha of whatever composition 4% copper, I will call it as a C naught or a C1 composition let us say for your benefit. So we call this as C1 composition, and so that is the free energy of alpha, I can call it as G of alpha of C1 composition. And now this if you carefully look at it, that value is higher than the free energy of the two phase mixture which is given by this point. What is that? The line joining the common tangent line, which is a straight line, it always gives you at any composition between the two, it gives you what is the free energy of the two phase mixture. The free energy of the alpha is this, free energy of the theta is that, and a line joining the two is something like a rule of mixtures. This is what you do in composites. For example, I know the strength of the matrix, I know the strength of the precipitate or the second phase, and I want to know the strength of the composite, I simply draw a line joining the two and call it as a rule of mixtures and find out. Similarly, we can use the rule of mixtures, and this point on this line at any given composition will tell you what will be the free energy of that alloy containing two phase mixture. So this is the two phase mixture free energy. So this value is lower than that value, so that means there is a driving force for the alpha to precipitate alpha plus theta, am I right. So what is that driving force? That driving force is this driving force, this is what I can call it as delta G, and the same delta G I showed you just a while ago in the form of G versus T diagram. This is a GT diagram and this is a GC diagram or GX diagram. So in the GX diagram you can see if this is the alloy, and you can see that if I increase the alloy composition, take it more and more towards theta composition, what you will see? You will see larger and larger driving force, and that is what you see here, that if I come to if I keep on increasing the alloy composition, I would see more and more driving force. Or for the same alloy, if I change the temperature, instead of this temperature I come to this temperature or this temperature, the lower the temperature, the more the theta is stable. you would see that this point, the what is called the equilibrium composition of alpha in equilibrium with theta shifts to the left, as you can see here, shifts to the left to such an extent that this difference will keep on increasing, the difference between your Li composition and the composition of alpha. If that increases, then you will see the driving force will increase. So you have a driving force, and which is what is this. This is all the driving force that you have. So at any given temperature I can talk about what is the driving force, and but though you have a driving force, you have a barrier, and the barrier in this case is the surface that has to be created, the new surface that has to be created, and the strain that the sample has, and the phase, the new phase that is coming out. Depending on which phase that is coming out, you have different strain. Depending on what is the structural difference between the parent phase and the product phase, the strain is going to depend on, and that is the reason why actually the choice of various structures come into picture. That is the reason why the system chooses the triple junctions and the grain boundaries for the nucleation is because the triple junctions are the region which are in a high energy state. First and foremost, they are in a high energy state. As a result, the system can easily relax to a low energy state if the nucleation can occur there. Second is that these are the regions which have more random structure. As a result, the strain can be easily accommodated much more easily at that grain boundaries. On the grain boundaries and triple junctions, you, because of the randomness that is available, because of the open structure that is available, the strain can be easily accommodated, and as a result you will see most of the nucleation occurs at the grain boundaries or the triple. In fact, when you go by the hierarchy of nucleation or hierarchy of the energy, you will always say the triple junctions are the highest, then comes the grain boundaries. Okay. Of course, the surface comes the first, this surface is the first, this is where the first nucleation will occur, surface is the first, and then number 2 will be the triple junctions, number 3 will be the grain boundaries. Grain boundaries are the where 2 grains meet, triple junctions are where 3 grains or more than 3 grains meet. So that is what is. So this is a triple junction where this are meeting, and whereas this line is where 2 grains are meeting, that is what we call it as a grain boundary. So that is how these are the regions where you have a nucleation taking place. But the problem that we have is, fine, nucleation is occurring, but because of the nature of this the theta phase, once it nucleates, it grows along the grain boundaries, and once it grows along the grain boundaries, it forms a thin network at the grain boundaries. It is like if you imagine the grain to be something like spherical, you would see a kind of a layer forming on the sphere, and once this happens, you will see, because this is a intermetallic phase which is a brittle phase, any crack that is nucleated at this place can easily grow through the intermetallic phase, and as a result what you get is a intergranular cracking, and that makes the alloy very brittle, and this is what we do not want, and that is the reason why in high carbon steels you see the presence of cementite at the grain boundaries of the austenite makes the high carbon steels very brittle, and that is the reason why we do certain treatment. What is the treatment we do? Spheroidization we do, or even we do another treatment other than spheroidization, any other treatment which does not take as long as spheroidization. High carbon steels, plain carbon high carbon steels, what is the treatment that we do to take care of this problem of continuous networking of cementite at the grain boundaries? Normalizing, as simple as normalizing. You simply heat the steel to the austenizing temperature, cool it rapidly, so that there is no time available for all the cementite which can come under the equilibrium conditions, which can come according to the lever rule. You do not have sufficient time for all the cementite to come, and it nucleates, and there is not sufficient time for this nucleated cementite to grow and cover the whole grain boundaries. So what you get is a discontinuous network of cementite rather than the continuous network, and that discontinuous network, which is what looks something like this. You have discontinuous network of cementite, something like this. Once you have that kind of thing, there is no continuity of the brittle phase at the grain boundaries, so intergranular fracture can be controlled. So this is one way we can control that. The other way to do is, if I can somehow prevent the precipitation at the grain boundary at all, that is the whole crux of precipitation hardening. I somehow try to avoid precipitating at the grain boundaries. How do I avoid this? The only way I can avoid is allow precipitation to occur not near the Solvus line, but at temperatures much below the Solvus line. How does the precipitation does not occur at if the precipitation is occurring at much below? For example, if the precipitation is occurring at this temperature, let us say, instead of at this temperature, let us say I call this as a T2, instead of T1, if the precipitation is occurring at T2, what is the difference between the two? Ultimately phase diagram shows only theta phase, theta has to nucleate, but the theta nucleation at the grain boundaries at temperature T2 is not easy. Why? Because if you want nucleation at the grain boundary to happen, the copper atoms, because you remember what is the alpha phase? Alpha phase has 4% copper. What is theta phase? Theta phase, if I talk in terms of weight percent, it is approximately 55% or so, is not it? So basically if you want to convert it into atomic percent, it is 63.5 divided by 2 into 27 plus 63.5, 1 atom of copper, 2 atoms of aluminum. So if you anybody has a calculator, you can simply do this. This is something like about 54 plus 63 is about 120, let us say. So it is 63.5 by approximately 120. So that turns out to be more than 50%, whatever it is, approximately 55, that is what I said. That is the composition. So that means you need copper atoms to move from the center of the grains to the grain boundary, such that the copper gets enriched at the grain boundary to the level of 55%, so that the alpha can theta can nucleate. That means from the center of the grains you need the copper atoms, and copper atoms are substitutional elements, they are not interstitial elements. So their diffusion rates are not very high, and you are talking of temperature which is very low, and because of this you see that the diffusion of copper atoms to that particular grain boundaries is not, because we are talking of grain sizes of the order of, let us say, a few microns. Most of the alloys, whenever you do solutionizing and cool back, they are of the order of 100 microns. So if you think 100 microns is the grain size, 50 microns is the diffusion distance. 50 microns is a very very large diffusion distance for the atomic diffusion, and if that is the case, then you see that at this temperature there is no problem, because the temperature is high enough where the diffusion rates are high enough, whereas at this temperature it is difficult. And because it is difficult for the atoms to diffuse up to the grain boundary, to nucleate at the grain boundary, but at the same time there is a driving force. Alpha does not want to remain as alpha. For example, if I take this alloy, heat it to this temperature, make it a single phase solid solution, bring that single phase solid solution to this temperature, and I am holding, let us say, I undercool it, I quench this alloy to this temperature and hold it there, like what we talked about undercooling during liquid to solid transformation. Similarly, if I undercool that alpha to this temperature, and now precipitation has to happen, at that temperature there is a large driving force for the precipitation. According to this, there is a driving force, and this is at T1. If I draw it at T2, the same free energy composition diagram, you would see the driving force is still larger. There is driving force, so alpha cannot remain as alpha, but the problem is there is diffusion is slow. Then the only solution for the alloy is that precipitation should occur inside the grain. that is the only solution. And if precipitation has to occur inside the grain, then you need to consider this and this very carefully. Strain energy becomes very important, surface energy also becomes very important. If the precipitation has to occur inside the grain, a new interface has to be created. At the grain boundary, you can say the grain boundaries are already high energy regions, so nucleation can occur, so this energy can be reduced. But if it is within the grain, the nucleation has to occur somewhere here or somewhere here. Imagine, then you need to create a new surface. That is where the system will choose that particular structure which has a lower interfacial energy and lower strain energy. And that is where you would see that instead of alpha giving you theta, where the theta crystal structure is orthorhombic, am I right? The theta is orthorhombic and theta has to come out of alpha, which is an FCC. From an FCC an orthorhombic structure should come out, and that is not easy. So the system will choose and that is not easy because the interfacial energy for such a transformation between alpha to theta, interfacial energy is very large. So for that interfacial energy being very large, the system will try to choose, is there any alternative for me? Are there any possible transient phases which can have a lower interfacial energy? So it starts looking for transient phases, which are metastable phases of course, but looks for those which have a lower interfacial energy, and that is where you come across something called GP zones. So the alpha precipitates what are called GP zones inside the grains at different regions, and the only heterogeneous nucleating sites here are what? Yes, dislocations. Anything else? I was talking to you earlier on the hierarchy of nucleation. I said surface first, second is the triple junction, yes, triple junction, then the grain boundary, then comes what you have just now said, stacking faults. After that comes your, what is the previous answer that you gave? Dislocations. After that comes what? Vacancies. Perfect. These are all the hierarchy of nucleation, and the surface energies actually decrease in this order, and that is why in fact if your sample has a lot of quenched in vacancies, vacancies can themselves act as nucleating sites for such nucleation to occur, or dislocations can be there, or stacking faults can be nucleating sites. So this is how you see a GP zones come out. The reason GP zones come out is GP zones are nothing but copper rich clusters. They are copper rich clusters, and copper rich clusters have, copper has what structure? FCC. So that means inside an FCC matrix another FCC phase is nucleating, and when an FCC nucleates inside another FCC, obviously the surface energy is very low. The only problem now is the strain energy. Why? Because the lattice parameter of copper is different from the lattice parameter of aluminum. There is definitely some strain. So it will choose that particular shape which has the lowest strain energy. So shape determines to a large extent the strain. I do not know whether you have come across, for example, if I look at different shapes, if I take a spherical shape, if I take a plate like shape, if I take a needle like shape, either this could be something like this, or it could have cylindrical, whatever it is. If you look at these three shapes, each of them have different strain energies. Strain energy basically is what is the compatibility of the precipitate with respect to the matrix. That is what determines the, if at whenever you have a spherical shape, spherical precipitate sitting inside a matrix, the strain energy is always the maximum. because the unit cells of the matrix cannot have compatibility, because they cannot have continuity. For example, whenever you look at a matrix inside which you have a precipitate, if the lattice planes inside the precipitate and those inside the matrix, if there is a continuity, then we will see the strain energy is the minimum. When do you have this? You have this when the lattice parameter of the precipitate and the lattice parameter of the matrix are exactly the same. Whenever you see the lattice parameter of the matrix and the precipitate are exactly the same, and this is what we call it as misfit. It is called a misfit, and this is given as A lattice parameter of the precipitate minus the lattice parameter of the matrix divided by the lattice parameter of the matrix in terms of percentage multiplied by 100, let us say. And obviously we look at the absolute value of it. It can be negative, it can be positive, we look at the absolute value, and when this is very very small, you see that there is a continuity. And even if it is a sphere at that, and whenever you have a misfit very small, strain energy is very small, and when the strain energy is very small, the system will choose that particular shape which will reduce the surface energy. What is the shape that will have the lowest surface energy? Sphere. That is the reason why in some of the systems you get spherical precipitates. Are you aware of any system where you have spherical precipitates? Any solid state transformations where you get spherical precipitates? Gamma gamma prime. Ni3Al, when it nucleates inside the nickel based matrix, you always see spherical precipitates initially, and when they grow they become cuboidal. Initially they are. Similarly, aluminum lithium phase diagram, if you look at it, Al3Li precipitates inside the aluminum, again spherical. Aluminum silver phase diagram, you have a phase called Al2Ag, again spherical. It is all because there the interface, the strain energy is minimum, so it chooses that particular shape which can minimize that. If the strain energy is large, then what it chooses is, it chooses that particular shape which has the minimum strain energy by choosing the shape, and that particular shape is, if you plot the strain energy delta G epsilon as a function of shape aspect ratio, if you plot, you will see that you get something like this. This is where the aspect ratio is 1, this is aspect ratio very large, and this is aspect ratio very small. This is what we call it as disk, this is what is sphere, and this is what is called a rod. Aspect ratio means the length versus the width of it. If I look at it, sphere obviously will have 1, and disk, that the length, the height is very small, whereas the length is very large, so it is less than 1. So you will always see wherever the strain energy is more, the system will choose a disc shaped precipitate, and that is what GP zones are. All the precipitates in aluminum copper system, the theta double prime, theta prime, all of them are disc shaped or plate like. So plate can have a best kind of compatibility when compared to either a sphere or a rod. So that is the reason why you see this happening. So the shapes of the precipitates depend on these two, because ultimately this has to be minimized. The system wants to minimize this overall thing because both are positive. This has to be somehow minimized, and if you can minimize this, this driving force that is available can be utilized for the precipitation. As long as this is larger than this, you can never have precipitation, and that is how you see the GP zones come out from first in the aluminum copper, and these GP zones as they grow, because the final equilibrium is theta, and GP zones are nothing but copper rich precipitates are on this end of the phase diagram. Okay, we are only up to 55 atomic percent here, we have to go up to 100% to get to copper, and this copper rich precipitates slowly change their composition and their structure towards the structure of the theta in steps, and that is how you see the GP Jones, the supersaturated solid solution becomes GP Jones, then theta double prime, then theta prime, then finally theta. We will stop here and take up later.